In the last video, we had understood nucleophilicity and versus basicity. So now we'll include one more point. Nucleophilicity or a nucleophile is responsible for nucleophilic substitution reactions, and basicity or a base is responsible for elimination reaction. Since the same anion can be a nucleophile, can also be a base, therefore substitution and elimination reactions are always under competition. They are in competition. They fight with themselves. So this is the additional point. Nucleophile causes the substitution reaction, base causes the elimination reaction, and both of them are nothing but an anion. Therefore, substitution and elimination are always competitive with each other. So which will dominate? Which will win the race? Which is going to win the race? Which is going to lose the race? Is decided by reaction conditions. Reaction conditions will decide between these two who is the winner. When I say reaction conditions, I consider reactant, I consider reagent, I consider solvent, I consider temperature. All of them togetherly comprises a reaction condition. So based on this reaction condition, we will decide which of them is going to win the race. But they are always competing with each other. So this is the last point of nucleophilicity versus basicity. Now look at the trend. Look at the trend first across the period. Across the period, what happens to nucleophilicity and what happens to basicity? Suppose if I give you carbon ion, methyl carbon ion, NH2 minus, amide ion, hydroxide and fluoride, and if you look at the trend of the nucleophilicity and trend of the basicity, what will happen, whether it increases or decreases across the period. So first of all, CS3 minus, look at their electronegativity. Carbon, being the less electronegative atom, will suffocate, will cry with this negative charge. It becomes a burden on him. He cannot withstand this pain because of less electronegativity. Electronegativity of fluorine is high, carbon is less. So being a less electronegative atom, he cannot bear this negative charge, therefore he wants to get rid of it. If he gets rid of this negative charge by giving these electrons to the carbon, then we call him nucleophile. Therefore, nucleophilicity of CS3 minus is greater than, NH2 minus is greater than, OH minus is greater than F minus. On what basis we have decided? Electronegativity is the reason. Electronegativity is, there might be other way to explain this, but I feel this is the easiest way. Look at the electronegativity. Being a less electronegative atom, carbon will suffocate with this negative charge. He feels burden, therefore he wants to get rid of that. So if he gives that electron density to the other carbon, then we call him as a nucleophile. Therefore electronegativity is the reason. Basicity, you look. In order to consider the basicity, write their corresponding acids, CH4, NH3, H2O, F minus. These are the acids, these are their conjugate bases. Therefore, among these four acids, by using your common sense, you can predict easily this is the strong acid. When this is the strong acid, your common sense will also tell immediately this is a weak base. And this is the weak base, therefore this must be a strong base. This is a strong acid and this is a weak acid. Therefore, what is the basicity order? Basicity order is also CS3 minus greater than, NH2 minus greater than, OH minus greater than F minus. Therefore, nucleophilicity and basicity are parallel to each other. The trend of the nucleophilicity and the trend of the basicity, both of them are same. Therefore, we conclude nucleophilicity and basicity parallel to each other. Where they are parallel in a period. So this point you just print in your brain. you print in your brain. So basicity is decided by the strength of the base or stability of the base, and nucleophilicity is decided based on electronegativity. This is across the period. When there is a period, there will also be a group. Therefore, what is its trend? What is its trend across down the group? Take the ions: fluoride ion, chloride ion, bromide ion, and iodide ion. Imagine these are existing. Where they are existing? They are existing in a polar protic solvent. What is a polar protic solvent? Water, alcohol, acid. All these are polar protic solvents. These are polar protic solvents. So a polar protic solvent can solvate an anion. Means he surrounds the anion. He solvates the anion. So from your periodic table knowledge, down the group size is going to increase. Therefore, fluoride ion is the smallest atom, whereas iodide ion is the largest atom without the water. Without the water, fluoride ion is the smallest one and iodide ion is the largest one. As if you proceed down the group, size increases. But as soon as when they enter into water, water is a polar protic solvent. When they enter into water, being a polar protic solvent, it hydrates. And you must have studied in your chemical bond, hydration is inversely proportional to size. Therefore, in the water, size of the fluoride is greater than size of the iodine. Size of the fluoride increases. Size of the iodine is smaller because of hydration. More number of water molecules surrounds, more number of water molecules protects F minus. Inside this there is a water molecule. Here also water molecule. I clearly told you in the last class, in the last video what we had seen, nucleophilicity is affected by steric crowding. Nucleophilicity is affected by bulkiness of the group. So this is bulky. Being a bulky group, being a bulky atom, it cannot approach the carbon easily. Being the small atom, it can approach the carbon easily. This whole drama is happening in water. The tendency of him to approach the carbon, he is also approaching the carbon. He is approached easily. He approaches the carbon easily. Therefore, he is a strong nucleophile. Whereas he is going to be weak nucleophile. Where? In polar protic solvent. In polar protic solvent, iodide ion is a strong nucleophile. It is a strong nucleophile because of its lesser size. Its size is less because of hydration is less. Because hydration is inversely proportional to size. In the presence of the water, fluoride ion is hydrated more. Therefore, size increases. Therefore, we had come to a conclusion. In PPS, polar protic solvent, nucleophilicity, fluoride less than, chloride less than, bromide less than, iodine. Then what about basicity? F minus, write its acid, HF. Cl minus, write its acid, HCl. Br minus, write its acid, HBr. I minus, write its acid, HI. Therefore, you know from your previous knowledge, this is a strong acid, whereas this is a weak acid. Therefore, this is going to be strong base. This is going to be weak base. Therefore, basicity order F minus greater than, Cl minus greater than, Br minus greater than, I minus. So this is the conceptual approach towards the basicity and nucleophilicity in PPS. In polar protic solvent, the most important point. This is the most important point for competitive examination. Fluoride ion is a bad nucleophile because of the hydrated fluoride ion size is larger. I minus is a weak base because the corresponding acid is stronger. So F minus due to large hydrated size, due to weak base. So this is about polar protic solvent, and remaining details we will see and we will cover in the next video. And just watch the videos and try to understand chemistry little more conceptually. And if you like the video, just subscribe the channel and enjoy the chemistry. I hope you will definitely learn concepts extraordinarily here. Thanks.